maybe several times. A farmer wants to fence in a rectangular plot of land adjacent to the north wall of his barn. Okay, somewhere barn. I don't know, it doesn't have to be exact. Okay, and the rectangular plot somewhere here. No fencing is needed along the barn. Okay, and the fence along the west side of the plot is shared with a neighbor. So maybe let's say this is west. So here is a rectangular plot of land, and this one will be shared. The cost will be shared for this. Fence. Okay, if the fencing costs $20 per linear foot, so 20 linear foot to install, and the farmer is not willing to spend more than 6,000, so that's the constraint. So the cost goes in this, and there is no needed here. So let's write down, this is x, this length is x, and this is also x. Okay, and this one is y, and nothing needed here. Then the total cost is 6,000, and per linear foot is 20. So the cost for this one, so the cost for this fencing will be 20 times y. So that's the 20y. Here is 20 times x, 20x. No fencing needed here, and the cost will be shared with a neighbor. That means not $10, it will be now, sorry, not $20, it will be now $10, I meant, so 10x. Or you can do half and multiply by 20, same thing, 10x. So let the dimensions, so we assume let the dimensions, because at the end of the day we are asked to find the dimensions of the plot. Okay, this is the plot. Let the dimensions of the plot be x and y. Now we have the constraint about the cost. So we already decided here, this is 20x, 10x, that's 30x plus 20y is equal to 6,000. Now let's simplify and solve for one variable. 30, 20, 6,000. We can divide through by 10. If we divide through by 10, then we get this. Now subtract 3x from both sides, divide by 2, so that we can isolate y. So y is 600 minus 3x all over 2. Later, when we find the value of x, we come back here and determine the corresponding y. Now we want to most area, we want to maximize the area. So this area is the objective function. So objective function area, we can write f or a, it doesn't matter. A equals, so how do we find area of this rectangular plot? Just length times width, x times y. Now y can be replaced from this constraint, okay, which is x times y is 600 minus 3x all over 2. Now we can distribute this to outside, we can just put like 1/2, and when we distribute, this is 600x over 2 minus 3x squared over 2. I separated into two fractions as well, which can be simplified as 2 goes 300 times. So 300x minus, we can write 3 halves x squared. Okay, this is our objective function. Now we want to maximize this. To minimize or maximize, we find the function's derivative. Okay, that's the calculus part. So far just algebra. Now we want to find the derivative, which is 300 minus 3 halves times 2x, and 2 and 2 cancel, 3x. Now we set the derivative 0 to find critical numbers, means the location or x values where we get maximum or minimum. So setting this 0, subtract 300 from both sides and divide by -3. So x is -300 divided by -3, because -3 times x, so we need to divide. -300 divided by -3, that's 100. Okay, so this is the answer, but we need to make sure this x equals 100 indeed maximizes the area of the plot. So we got answer, but we'll confirm, and we plug this back here to find the corresponding y. That is 600 minus 3 times 100, 300. 600 minus 300 is 300 divided by 2, 150. Okay, now to see x equals 100 indeed maximizes the area, because our objective function is the area. Okay, let's use second derivative test. Okay, to see x equals 100 maximizes the area, objective function, the area function. So let's find second derivative. Okay, that is derivative of first derivative. So what is its derivative? That's 0 minus 3x is -3. So the derivative is -3. So second derivative negative for any x, in fact for this x as well, so less than 0. So whenever we have a function less than 0 throughout whatever the domain is, then we get concave down. So the graph, the objective function graph, looks like something like this. And our x equals 100, that's in fact a critical number, so that gives us this function value at x equals 100. So that means maximum. The area is maximum at any x, in fact, because second derivative is -3, and we got this critical number at x equals 100. Okay, so this line shows x equals 100 indeed maximizes the area function, area of this plot. Thus we write down the final answer. The dimensions, length and width, x, y, we found x equals 100, so it's a fit, and y, plug in here, plug in the x value, we get 150. Final